Right. Thanks everyone for joining us today. It is my pleasure to introduce Lawley. Zhang is an associate professor in the Department of Mathematics at University of Utah. His research focuses on probability and stochastic processes with applications to cell biology. So today he will tell us about how to use stochastic analysis to study problems from pharmacology and human fertilizations. Zhang, please go ahead.
All right, yeah, thanks for the invitation and opportunity to talk. So I want to talk about two pretty different problems. They're different mathematically and they're different in terms of their application. But I couldn't resist telling you about both of them. Perhaps the one thing that unites them is they're both. I think we'll see that looking hard at a biological problem. This leads to new questions in stochastic processes. So that's kind of maybe the one uniting element that looking hard at these biological applications leads naturally to some new questions in stochastic processes. So what are the two problems? So it's in medication non-adherence and extreme first passage times. So this is just a broad outline of these two areas. So the first one is as Ying says from pharmacology, and then the next one is dealing with something called redundancy, or sometimes called the redundancy principle, and maybe I'll just jump right into the first topic, and it's about medication non-adherence, or sometimes called non-compliance. So the point of this slide is just to tell you what medication non-adherence is, and to tell you that's actually in fact a very big problem. So medication adherence is the extent to which patients take their medications as prescribed. This is patients sort of doing what their physicians tell them to do, taking medication on time, the right amount when they're supposed to do it. So medication non-adherence is actually a very big problem. There's all kinds of statistics you can look up for this, which I think make the point very clear, but here are some summary statistics. It's estimated that more than 100,000 preventable deaths every year in the United States are caused by medication non-adherence. And it's estimated that it costs more than $100 billion in preventable healthcare costs every year as well in the United States. In fact, perhaps it might make the point even stronger is there's this quote from the World Health Organization in 2003, which I find quite a remarkable quote. And they say that increasing the effectiveness of adherence interventions may have a far greater impact on the health of the population than any improvement in specific medical treatments. I think that's a pretty astounding statement. They're saying that, you know, if we could just have our patients now take their medication as prescribed, adhere to these interventions, then that would actually have a better impact on public health than any new advances in medical treatment. So that's even better than making new drugs and new treatment, new diagnostics, if we could just have people follow the existing treatment. So it's pretty strong statement. And then I like this last quote is from a former US Surgeon General, just put real simply that drugs don't work in patients who don't take them. So I think that's something we can all understand. And so this is a really big problem. But what I've been surprised to see is that very little mathematics has been applied to this problem. And I think math is in fact a very good tool to use to understand and combat medication non-adherence. Specifically, I'll just point out because the great thing about math, as opposed to what would be another way you might want to study or combat medication non-adherence, right? Maybe you would want to do a clinical trial, right? But it's not ethical to have clinical trials where you force patients to miss doses of medications they need. Right? So it's hard to study in a clinical setting, and I think math is a very good tool for it. So let me look at sort of a simple model that tries to answer this question. I think this is probably a question that probably everyone in this seminar has faced before. So what do you do if you miss a dose of medication? Okay, so suppose it may be like a medication that you've been on for a long time, or maybe it's a sort of shorter term medication, but the simplest way to think of it is suppose you're supposed to take this drug every day, and you wake up today, Wednesday morning, and you realize, oops, I forgot yesterday. So I'm supposed to take it every day. This morning I wake up, I just realized I didn't take it yesterday. So what should I do? Should I skip the missed dose? So I was supposed to take it yesterday, should I just skip it? Should I take a double dose to compensate, right? So today's Wednesday, I forgot my dose from yesterday. I'll take the one from yesterday in addition to the one today, right? So I'll take a double dose to compensate. And some of these references at the bottom of the slide just are some papers that are where they're arguing that patients often do not receive instruction on this question. So I think it's a very natural question, common question. Probably most of us in here have forgotten missed medication before and have asked this question. So now I want to propose a simple model to analyze and try to answer this question. And I think we'll see remarkably that we'll write down a very simple model, and already we'll get into some pretty interesting mathematics. So here's I think a very natural, very simple model. This is a pharmacokinetic model, and there's these two parameters we'll start with: the dosing interval and the half-life of the drug. So in this model, the patient is supposed to take a dose of the drug. We'll scale it to be 1, a unit-sized dose of the drug every t-naught units of time. And so if you're supposed to take it every day, then t-naught is 24 hours. You're supposed to take it every t-naught units of time, and we'll assume that the amount of drug in the body decreases exponentially with some half-life called t-half. And it'll be useful to define alpha, which is 2 to the minus t-naught over t-half, which is simply the fraction in the body after time t-naught. So if you take a dose of size 1 at time 0, then at time t-naught, at the time for your next scheduled dose, you'll have alpha remaining of the first dose you took. Okay, so let's think about this a little bit. Let's think about for the perfect patient. So how would the amount of drug evolve in time in the perfect patient? So immediately after you take your first dose, you have one unit of drug in your body. And then immediately after your second dose, how much do you have? Well, the first dose that you took before has decayed now. You now have amount alpha of that left. And then you just took the second dose. So you have all of that left. So it's alpha plus 1. And then you can see sort of what's going on here right after the third dose. So how much do you have? Well, the first dose you took in your body now has alpha squared left. The dose you took, the second dose, now has decayed to alpha, and then the third dose you just took, you have 1. And so after many doses, take it for a long time, the amount of your drug in your body is this geometric series. I'll call it a perf, because this is the perfect patient. They always take the drug as they should. And of course, it's a simple geometric series identity. It's 1 over 1 minus alpha. Okay, but now let's think about a realistic patient, a more realistic patient where sometimes they miss doses. And so we're gonna propose, I think, what is perhaps the simplest model for an imperfect patient. And we'll simply assume that this imperfect patient, at every dosing time, they either remember or forget to take their dose. So at the nth dosing time, the patient remembers to take their dose with some probability p. And if that happens at time n, at the nth dosing time, we'll write xc sub n equals 1. So that corresponds to the patient remembering their nth dose. And then they forget with probability 1 minus p, in which case, denote that by xc sub n equals 0. And our analysis will allow for correlations in these doses. So maybe if you missed your last dose, you're more or less likely to take the current dose. But for now, we'll assume that you remember and forget each dose independently. And then so if f sub n is the amount taken at the nth dosing time, then the amount of the body I'll denote by capital A, and it comes out as now this random geometric series. So it's useful to index time starting here. So the present is time 0, and then you're going backward in time -1 and -2. And so the way to read this is, sitting here at the present, you have what you just took, f naught, and then what you took at the previous time, f sub -1, that's decayed to alpha. What you took at the time before that is f sub -2, and that's decayed to alpha squared, and so on. And then the amount of drug now, after you've been taking it for a long time with this random adherence, is this series here, where these f sub minus n's are these random variables which depend on whether or not you remembered or forgot. And the important point is we're modeling adherence by a random process, which I think is quite natural, right? You usually don't miss doses in a precise, predictable pattern, but it's random in nature. And so now the amount of drug in your body is also going to be random. And so what we want to do is we want to study this random variable, which is the amount of drug in your body for a long time. And we'll study this random variable under 2 what I call dosing protocols. So this first one in red here at the bottom, I'll call the single dose protocol. And in that protocol, F sub n, super single, is just 0 or 1, depending on if you remembered or forgot. And what that means is, so if you forget at time n, of course, you don't take anything. And if you remember at time n, then you take a unit dose. So in particular, this is I call the single dose protocol, because you only ever take a single dose, even if you forgot it the previous time, right? So this is the answering the question, what should I do if I miss my previous dose? This is, you could think of as, this says skip your previous dose, just take what you have now. And then so I'll call A super single, this random amount of your drug in your body if you're following this dosing protocol. And then the other dosing protocol I'll call the double dose protocol. So what do you do there? Well, if you forget at time n, like C sub n is 0, then of course you don't take anything. If you remember at time n, and you remembered at time n minus 1, then you just take a unit dose, right? So if I remembered now and I remember my last time, I'll just take 1 now. But so what makes it different here is, now if I remember at time n and I happen to have forgotten my previous dose, then I'll take an extra dose to compensate. So I'll call that the double dose protocol, and similarly I'll call ACE with the superscript double be the random drug amount in your body if you've been following this double dose protocol. Okay, and so what we really want to do is understand the statistics and the distributions of these two drug amounts in your body under these different protocols, and understand, sort of try to say which one would be better for the patient. How does that depend on the various parameters of the problem? All right, but before I do that, I want to just spend one quick slide telling you that even though this is, I think, a very simple model, probably a pretty natural one, it already gets into some pretty exotic mathematics. So in fact, this random variable A, what I'm calling A single, is something that's called an infinite Bernoulli convolution. And this random variable has been studied in the pure math literature since the 1930s, beginning with Paul Erdos and others. And of course, they when they studied it, they weren't thinking about drug adherence. They weren't thinking about models of these pharmacological models. They were just studying this mathematical object for its because it's interesting mathematically. And I'll just give you a quick sense of that on this slide. So the reason it's interesting is that the distribution is often singular. So the distribution of this random variable is neither continuous nor discrete in many situations. Give you a flavor for some of the types of things that have been proven about this. So if P is a half, so that is you miss each dose with probability half, and alpha is this particular somewhat strange value here. Alpha is this decay rate. Okay, so in that particular case, the distribution is singular. If P is a half, but alpha is bigger than half, then the distribution is continuous for almost all alpha. Other statements, if P is not a half, but it's close to a half, then the distribution is either singular or continuous, depending on exactly what the alpha is. Now, these particular facts aren't going to be so important for our application to pharmacology, but I just want to point out that here we start with a very natural medical question, and already we're just a few calculations later, we're into some pretty exotic and interesting mathematics. So this is all for the single dose protocol. And the double dose protocol is actually a bit more complicated, because now in the double dose protocol, there's correlations between the terms in this random series. So the analysis is in fact quite a bit more complicated. Okay, so that's just telling you about why this is interesting mathematically and some of the history of the problem. Let me jump back to the pharmacological application and see what we can say about this model. Okay, so we have these three quantities. We have A perf. That's the amount of drug in the perfect patient, right? So this is somehow the goal. This is what you want to be at. You have A single, that's the amount of drug in the patient who they skip a missed dose, and A double, the amount of drug in the patient who takes a double dose to compensate for a missed dose. So I'm going to define these statistics, which I'll call deviations, and the deviation delta single for the single dose protocol, and deviation delta double for the double dose protocol. And so what are they? Well, it's meant to be just some measure of how close the amount of drug in your body is to the perfect patient. And so you want to have a small deviation. So I define it to be, for single, it's A single minus A perf, so how far away you are from the perfect patient, square it, take expectation, and then you just square root it and scale by the scale of the perfect patient. So it's in that way, it's similar to a coefficient of variation, but the sort of the target amount is this perfect patient. And then analogously, we define a deviation for the double dose protocol the same. And so now, so you can find for this model, you can find explicit formulas for these deviations for the single dose and the double dose protocol. I won't show you those. They're fairly complicated, and the derivation is a bit technical. But I want to tell you kind of the implications from this analysis and give you a kind of an intuitive feel for why it is what it is. Before I do that, I want to ask a question. So it turns out the size of the deviations depends on the half-life, how the half-life compares to the dosing interval. So I want to ask questions. So anyone you can feel free to speak up or post in the chat. But so let me first ask, if the drug has a long half-life, so T half is much longer than the dosing interval, and that means this alpha is close to 1, which dosing protocol has a smaller deviation? Put another way, if the drug has a long half-life, should you skip your missed dose? That is, should you follow the single dose strategy, or should you take a double dose to compensate for a missed dose? So what do you think? Anyone be willing to offer an intuitive guess here? What do you think? Half-life is long. Should you skip the dose or take a double?
I think take the double.
Okay.
That'll be my guess too.
Okay, awesome. Okay, good. Okay, so usually when I ask this question, I get the opposite response. But turns out that's what we see. The double dose has a smaller deviation for long half-lives, and then the opposite is true if the drug has a short half-life. And so this analysis is saying is the drug has a long half-life, take a double dose. If it has a short half-life, then just skip it. And it's interesting. So when I first started working on this problem, I called a good friend of mine who's a pharmacist, and I just started chatting with him, and I was asking him, what do you do if you have someone that says that, who asks you what should they do if they miss a dose? And he said, well, it depends on the drug and depends on the half-life. And I said, well, what if it has a long half-life? And he said, oh, if it has a long half-life, then you never take a double dose. You always skip it. And of course, that's exactly the opposite of what we're arguing here. So let me try to give you some intuition and try to convince you that this is right. So first, okay, so this is just a plot. I'm just plotting in blue and red these deviations as a function of this parameter alpha, which describes how the half-life relates to the dosing interval. So over here is a long half-life, large alpha, and you see the deviation is in fact smaller. Okay, so let me answer this question. So is taking a double dose toxic? Okay, so I think probably what would cause someone to perhaps be afraid or not want to take the double dose is they think, well, that's going to cause me to have too much drug in my body, right? If I take double what I usually take, I'm going to have way too much. But turns out that that's not true for drugs with long half-lives, which of course, those are the drugs we're arguing you should take a double dose in. So we can define this statistic, I'll call it lambda super double, and that's just the supremum over all patterns of remembering and forgetting. So this is the largest amount you can have in your body if you're following the double dose protocol, and compare that to the amount that you would have if you're following the protocol perfectly, if you're taking your drug exactly as you should. And it's this 2 over 1 minus alpha. So you plot that as a function of alpha, and that's a solid curve here, I guess that minus 1. And so what you see is if you're over here where alpha is big, half-life's long, then this maximum possible overshoot is only a few percent. And in fact, the solid curve is this maximum possible overshoot. It's the way that occurs is the somewhat pathological case where you're exactly missing every other dose. So you're taking a double dose every other time for a long time. And it's kind of, that's actually quite rare for that to happen. The more typical overshoot is this dash curve, which I'm not giving you the formula for, but you can work it out and see that's in fact much smaller. Okay, so let me now, before I sort of want to give you some intuition before this is true, let me tell you a way that we would like to apply this result. It's to this drug called levothyroxine. So levothyroxine is one of the most common prescription drugs in the US. So depending on the year, it's either the most highly prescribed drug or second or third, it's usually top 3 at least. Some years it's most commonly prescribed drug. So it's a very, very, very popular drug. It treats hypothyroidism. So a hypothyroid means your body doesn't produce enough thyroid hormone. And the standard treatment for hypothyroidism is you just take this drug, levothyroxine, which is a synthetic form of thyroid. You take a single dose of it every day for the rest of your life. So that's the standard recommendation. That's the standard treatment. And it's kind of the perfect type of drug for this analysis, because you have this regular prescribed dosing interval every day. So dosing interval of 1 day or 24 hours. And you take it for a long time. You take it for the rest of your life. That's the treatment. And if you Google, levothyroxine missed dose, you'll see lots of results. And the vast majority of them give the standard recommendation, which is to skip the missed dose, or in our language, as I presented, this would be to follow the single dose protocol. If you miss a dose, just skip it. But the half-life for levothyroxine is very long compared to the dosing interval. Half-life is about 9 days. It's much longer than the dosing interval of 1 day. You work out alpha, it's about 0.93. So our analysis actually would differ from the standard medical recommendation. Our analysis would say take a double dose after you miss a dose. And then if you use the formula from the previous slide about the maximum possible overshoot, at most you could have only 4% more than the perfect patient. So if you're taking levothyroxine, this very commonly prescribed drug, most sources would say skip a missed dose, but this analysis says you should take a double dose. That will make your sort of overall drug amount closer to the perfect patient, and you're never gonna have much of an overshoot, and most only a few percent. Okay, so why should you believe me? Well, I didn't give you the mathematical proof of these results, but let me try to give you a proof by simulation. I just try to give you some intuition. So here I'm plotting the amount of drug in a patient over time as a function of the dosing times. Here I've normalized it by the amount of drug in a perfect patient sort of right after you take a dose. So here's the perfect patient in black. Right, so you start here at steady state. Okay, right. So you take it goes down, take it again, it goes up. Right, so it's this sawtooth pattern. And the gray region is just the highlighted, between the peaks and the troughs. So for the perfect patient, here the alpha is from levothyroxine, this drug of interest. Okay, so here's a time course of patient following the single dose protocol. So you can see in the simulation, I have them miss doses randomly. I have something here, I think of the adherence percentage is something like 80% here, I think, for the simulation. So you can see, right, so you miss doses, of course, you go too low. And then here's now the solid blue is the same patient. They're missing doses at the exact same times, but they're following the double dose protocol. And the point of this slide is you can see the blue for the double dose patient, their curve, their time course much more closely approximates the perfect patient. And this solid line up, or excuse me, the dashed line up here, this is the maximum possible that they could ever have, this double dose protocol. So they're sort of meant to be kind of a proof by simulation, give you a sense for why you should believe this. Should be one more thing is that you can look at a histogram. So here I'm plotting an empirical probability density, where here the horizontal is the amount of drug in the patient normalized by the perfect patient. And so if you follow the single dose strategy, the distribution of the random amount of drug in your body is this sort of bell-shaped looking shape curve centered on around a little bit more than 80%. Here, this vertical line, this is the perfect patient, right? This is they have a sort of a delta function drug amount there because there's no randomness in them. And then the blue, this is the probability density for the amount of drug in the patient following the double dose protocol. And the point of this is just to show you that this blue probability density is a closer approximation to this perfect patient at 1 compared to the single dose strategy. And so this is kind of this is meant to give you some intuition why you should believe these results. So we're pretty pleased to see that write down this simple model, and you very quickly you can get some recommendations which are against the most common recommendations. In fact, and it's such a commonly prescribed drug. My guess would be in a group this large, I wouldn't be surprised if there's someone on levothyroxine, in fact, because it affects something like 5% of the world population. So
Sean, I have a question.
Yeah, please.
Do you know how well calibrated is the perfect dose amount? I mean, is a physician really just trying to make sure that you have between like 1/4 to 100% of that perfect amount? Does the perfect amount already build in that there's going to be some non-adherence? Just trying to get a sense of how important is it to be close?
That's a good question. Whether or not the perfect amount builds in some amount of non-adherence, I don't think so. and in terms of how they choose that perfect amount, I think that that's usually calibrated over time. So they measure TSH, thyroid stimulating hormone, in the blood after you've been taking it, and they sort of that's a proxy which allows them to infer the amount of thyroid you have, and so they kind of will, you know, an endocrinologist will look at that number, your TSH, thyroid stimulating hormone from the blood, and then compare that to what you've been taking, the amount of levothyroxine you've been taking, and try to get those just right. In fact, the reason I actually even know about this, even heard about this drug, is my mom has been on this for like 30 years, and so she often will go every year or so. We'll see her endocrinologist and kind of check where she's at for that. Yeah. Thanks for it. It's a good question. Are there other questions? This would be I'll transition to the other topic. So if there's, I'm happy to take questions at the end too, but now's a good time.
I had one more question, actually.
Yeah, please.
So one of the things, I guess, that, I mean, if we're talking about a kind of forgetful patient, then especially in sort of, let's say, people with neurodegenerative disease, you might also imagine not only they could forget to take a dose, but they might actually forget whether they took the last dose or not. So could you extend the model to also think about sort of also a random variable for whether they're remembering correctly or not? And do you have any idea of how that would change things?
Yes, terrific question, right? So yeah, they're forgetting to miss doses, and so maybe they wake up and they think, well, I think I missed yesterday, so let me take an extra one, but in fact I didn't. So we could definitely model that, right? We include, you know, with some probability, you know, that they do that, and we could look at that. Yeah, so that I think that may be in fact why this single dose protocol is more commonly prescribed, just because it's kind of simpler and you avoid that possibility. But I think, you know, a lot of people who are on a medication where they're supposed to take it regularly like this, they'll have, like, you know, weekly pill boxes, you know, their Sunday dose and their Monday dose, and so that would I think help a little bit in that way, right? If you open it up on today and you see, oh, my pill from yesterday is still there. And then I think just, if, you know, if someone asks the question, like, if I know I forgot, if I know I missed one, what should I do? Then I think, you know, this would be a way we can answer that. But yeah, that would be interesting to look at, like, see how much this changes if we, you know, with 10% probability they take an extra dose when they shouldn't. See what that does there. Yeah, that's a good idea. Well, maybe if there are no more questions right now, I'll keep moving. And
I have a brief question, Sean.
Oh, please, yeah.
Yeah, sorry. There are two ways in which taking a drug can be toxic. One is the amount that you have in your blood, and maybe one is the amount you have to process at once, like maybe the jump of your shot noise process. So I was wondering if you could extend the result to also control for a maximal amount you need to process. And so that would mean it's a slightly different protocol than the double. You could say if you missed a dose, maybe you can take 2 doses, but with some delay during the day, so that you need to be far away from the next dose, but also from the dose you take that day. I don't know if you looked at that or if it's relevant.
Yeah, no, I think it's definitely relevant. Yeah, I think it's a good idea. I think, you know, a related thing that your question makes me think of, which I think if we would have to address as well, is, you know, this simple model, we're only allowing, like, doses to be taken exactly at a dosing time, and so, like, there's no late doses or you know, doses taken between dosing times. So that would be, I think, another interesting thing to look at. And in fact, I'll point out for this levothyroxine drug, there are the majority of recommendations you'll see will be to say to skip the missed dose. But I have seen one, I think it's from the American Thyroid Association, where they say if you miss your dose from yesterday, what you should do is you should take your usual dose in the morning. I usually tell them to take it in the morning, and then take an extra dose in the evening, which is sort of exactly what type of thing you're suggesting. So I think it's a really, really good question, good idea. Yeah.
Okay, thank you.
I see. So there's a question in the chat. I can, yeah, since we're talking about it now, it says, if the dosage is very close to the maximum dosage suggested, the slight overshoot might be something that would be okay, might not be something that would be okay. How would constraining the allowed overshoot change the result as a function of T half? Yeah, so that's I think if I understand that question right, you know, I'm saying, you know, a few percent is not bad, but perhaps for some drugs, they really need to be tightly titrated, and there's a real thin, narrow therapeutic window. So yeah, that was another way to would be interesting to extend this. Think about that.
Thank you. Just like a quick add-on to that,
Yeah,
if, for example, I mean, I think it's correlated to what somebody was asking before, like if it's like not just one day you have missed, but like 2 days or 3 days, and how would that change like how you are modeling? Like it's more like, I know it's like P and then P square and something like that, but how would, like, is there like, how would you extend, like, yeah, that's the question.
yeah, it's good. Yeah, it's a good question. So in this model, in this double dose, you only ever take a double dose. In the paper where we present all this, we look at some other dosing protocols where, like, if you missed your 2 prior doses, you can take a triple dose, things like that, which are interesting. But you know, then another downside of that is then it gets more complicated. So you know, we're trying to battle the problem of patients not taking their medication as they should, and then we'll be a little wary of making dosing protocols too complicated. So that's, you know, that would be another aspect. But these are all really good questions and ideas. I think just as a general point, I think this is showing that in my view, like medication non-adherence is a big problem, and all these, you know, different questions, like, you know, what if the drug was a little bit different? What if it had different dynamics? What if, you know, this has a very simple pharmacokinetic model, but what if you had a more complicated pharmacokinetic model? How would some of these recommendations change? And these are I think all, you know, questions which are ripe for mathematical stochastic investigation. So maybe I'll go to the next topic, and I'm happy to at the end revisit any you know, this first application. Okay, so the second one is very different. So please forgive me, but you have to kind of change gears quite a bit here. So here the application is different and the math is very different. So that we're calling this redundancy in cell biology and extreme statistics. And I think the way I like to introduce this is with a question. And it's this kind of this question is specific to human fertilization, but it's kind of prototypical or characteristic of the types of questions which motivate this work. And it just asks, why do 10 to the 8 sperm cells search for the egg when only 1 sperm cell is necessary? And so why, in fact, it's about 300 million. So why do you have 300 million sperm cells when you only need 1 sperm cell to reach the egg to have fertilization? Again, there's similar situations happen in neuroscience and in gene regulation. For sake of time, won't discuss those too much, but the point is that there's in fact a variety of scenarios and systems in cell biology in particular, where you have this great discrepancy between sort of a very large number of what you call searchers, whether it's sperm cells or calcium ions or transcription factors. You have these sort of moving objects. You can think of them as searching for a target. You have these large number of searchers, but yet what matters only is when the first searcher finds the target, or the first 2, or something like that. And this is so this is generated quite a bit of work recently. In fact, some people have formulated what they call the redundancy principle. And the redundancy principle says that many seemingly redundant copies of an object, whether that object is a molecule, a protein, cells, etc., these many seemingly redundant copies are not a waste, but in fact they have the specific function of accelerating activation rates. So the quote unquote extra copies are necessary for biological function. So maybe in the context of human fertilization, if there's only 1 sperm cell, or 100 or 1,000 or 1,000,000, the fastest sperm cell wouldn't find the egg fast enough. but what you need is a very, very large number of searchers so that one of them will be fast enough. That's kind of the idea. There's some references here at the bottom, where they formulate this idea. It's a nice paper in PRL. It's the first one by Mearson and Redner, looking at this in a model of human fertilization. And there's this nice review by Schuss, Basniaki, and Holkman in Physics of Life Reviews. And then, in fact, their review paper generated a number of commentaries in the Physics of Life Reviews, kind of where they're commenting on this redundancy principle idea and arguing this is in fact a big idea which is kind of present in various biological systems. So this is what I want to talk about is for the remaining time. Some work we've done on this problem. And okay, so let me introduce it a little bit more formally mathematically. So the way we think about this is in terms of what I call extreme first passage times. So what's an extreme first passage time? Well, let me first talk about it. First passage time. First passage time asks a question: how long for a searcher? In this case, we'll talk about diffusion. How long for a diffusing quote unquote searcher to find a quote unquote target? So right, so here's a picture on the left, right? So the searcher starts at x naught, it diffuses around, and the target is maybe this red boundary. Or maybe on the right, it's diffusing in some bounded domain, maybe some model of some intracellular region, and it's looking for this target, some receptor or something there in red. Okay, so you can formulate this mathematically in terms of we call it first passage time, FPT. Tau, it's the infimum of all time such that x of t, so x of t is the random position of the searcher, this diffusion process, first time that it's in the target. And so there's lots and lots of work on first passage times, trying to understand timescales in these problems. Roughly speaking, if the target is big, then this expected first passage time, or mean first passage time, is something like the diffusion timescale, L squared over D, where L is the distance to the target. That would be kind of this picture on the upper left. On the other hand, if the target is small, like the picture on the upper right, with this small red target, then in 3D, the mean first passage time scales something like the domain volume over the size of the target. The point is that's much longer than the diffusion time scale. So I'm just giving you just a quick intro to some of these first passage times problems. Lots of really nice work done on these. But extreme first passage times ask a very different question. Those previous questions were asking how long it takes a single searcher to find a target. An extreme first passage time says how long does it take for the fastest searcher out of n searchers to find a target. So the idea is you have many searchers, capital N searchers where n is large, and the time scale of interest, like say in the fertilization example or in other biological examples, what matters is not how long it takes the average searcher to find it, but what matters is how long it takes the fastest searcher, which I'll define to be capital T sub capital N, which is the minimum of all these individual first passage times. So the taus are these individual first passage times, and T is the fastest one. And so for most of the analysis, I guess in fact all the analysis I'll talk about today, these taus are going to be IID, independent and identically distributed. All right, so the idea is you have capital N searchers, they're all searching for the target, but what matters, so the biological process is triggered or initiated by this fastest first passage time, or extreme first passage time. And the point is, if N is large, this fastest first passage time is much faster than a single one. And so in this sense, what matters is if you have a large number of searchers is the extremes of the distribution. The mean first passage time of a single searcher is not so relevant. What matters is this extreme first passage time. Okay, so what can we say mathematically about these? Let me just give you. I tried very hard not to make this talk too technical, but I wanted to do a real simple kind of back of the envelope calculation, which gives you a feel for why this problem is interesting mathematically. Just give you a sense for the asymptotics involved. So how might you estimate this fastest first passage time Tn for large n? Okay, so here's a calculation. So the first equality, the expected value of Tn is just this integral of the probability that Tn is bigger than T. This is the survival probability of Tn. This is an identity from probability theory. Second equality, this is just the definition of Tn, right? Tn is the minimum of all these individual taus. But then now, since the taus are independent and identically distributed, and since the minimum of them is bigger than tau, if and only if every one of them is bigger than tau, then we just get that this is the probability that a single one, tau, is bigger than T raised to the nth power. And then the final equality is, of course, just an algebraic identity, right? P to the n is the same as e to the n log p. The reason I wrote it like that is because if you're an applied mathematician and you see a formula, you see an integral of the form e to the large parameter times a function, right? You sort of have something well up inside you that says I should use Laplace's method, right? This is what we've sort of been trained to do. So you try to do naive application of Laplace's method and it fails. And it fails because in most problems of interest, these diffusion problems, this survival probability of a single first passage time is what's called a flat function at t equals 0. Flat function is a function which all the derivatives vanish. So p and all of it, this p of tau bigger than t, and all of its derivatives vanish at t equals 0. And so there's no meaningful Taylor series approximation, and so sort of a Laplace's method fails that. So you have to work a little bit harder. I just want to give that calculation just to give you a little bit of sense of the asymptotics in this problem. Okay, so let me talk about what's known. So what's known about these fastest first passage times? So there's a really nice paper in 1983 by Weiss, Schuler, and Lindenberg, where they look at this problem in one-dimensional domains, and they come up with this formula here. Expected value of the fastest first passage time in a one-dimensional domain has this large n behavior. So we'll see this formula a lot in coming slides. So let me talk about it. So L squared over D, right? That's the typical usual diffusion timescale. And then you have this decay come from 1 over log n. And then so what's L? L is the distance from the initial location to the target. And then, I should say this twiddle has the precise notation that means the ratio goes to 1. Right? So F twiddle G means ratio goes to 1. Okay, so that's 1D domains. And some of the other references I listed at the bottom are problems in other one-dimensional domains or what are effectively one-dimensional domains. And in fact, until recently, very little has been known in higher dimensions. So let me tell you a little bit about some of the work we've done on this problem. Okay, so I will. Okay, so we want to extend this to a higher dimensional domains. Let me just give you a kind of a proof by picture. So here's a very simple higher dimensional domain. It's very idealized, but let's start there. Let's do the simple problem first. So suppose you have the searcher start at the top of this cylinder and the target is a cylinder right in the bottom. So how do we do this? Well, so let me give you kind of a proof by picture. So in the black is a typical trajectory, right? Sort of wanders around, and eventually hits the target. This blue one is a cartoon for what the fastest searcher would do, and it would go roughly straight down to the target. So the way that we argue this precisely, and the formal proofs in the paper I list at the bottom, but what you argue is that, well, if you have many searchers, then this fastest searcher finds it fast. And if it finds it fast, it doesn't have any time to leave this thin tube which connects the starting location of the target. So therefore, if it doesn't leave that tube, the problem is one-dimensional. But I know the answer for the one-dimensional problem. Right? So what that says is for this three-dimensional problem, it has to scale like the one-dimensional problem. But I know the one-dimensional problem answer already. It's this L squared over 4D log n, where L is the shortest distance. Okay? Now that's, of course, for this simple idealized domain, but you can generalize it. If you use a more general domain, you apply the exact same argument, right? You draw a line from the starting location to the target and say, well, it can't leave this thin tube if it gets there fast, but if it doesn't leave the thin tube, it's a one-dimensional problem. And I know the answer for the one-dimensional problem. So that's extended to that. So that's what I call a sort of a probabilistic approach to this problem. One problem with this approach is that we only prove this using this method if there is a straight line path from the starting location to the target. So now let me give you some results where we can extend this quite a bit. Let me give you a theorem. So two theorems. I try not to make this too technical, but the first theorem says it gives some typical short time behavior of the CDF, the distribution of a single first passage time. And what the theorem says is under some general assumptions, I'm cheating a little bit, I'm not telling you what those are, but I'll give you those in a moment. Under some general assumptions, a single first passage time tau satisfies this short time behavior on a log scale. The way to read this equation star, by the way, is sort of here. Right? So equation star means very roughly, right? If you sort of unpack this log, it means that the distribution of tau is something like a to the p e to the minus L squared over 4 dt. And this a to the p up front doesn't really matter on the log scale, so it's approximately e to the minus L squared over 4 dt. And I'll just point out that this is kind of a prototypical example of a flat function. So if this function goes to 0 very, very fast as t goes to 0. In fact, all of this function and all of its derivatives vanish at t equals 0. Okay, so under general assumptions, a single distribution satisfies this, and where L is a certain geodesic distance. I'm again cheating, I'm not telling you what that is yet, but I'll tell you by example in a moment. But then this next theorem says that if star holds, right, so if I have this short time behavior of a single first passage time, its distribution, then I can get the large n behavior of every moment of the kth fastest first passage time. So this is some new notation. So before I was talking about the fastest first passage time, you can generalize it to be the kth first passage time. And what this says is the nth moment scales like the same L squared over 4d log n to the m. And this is as you have many limited many searchers. Okay, so in these next couple slides, in the next couple of minutes, let me show you what are some ways that we can do this. So we can apply this theorem if you have a situation where you have diffusion with obstacles. So maybe this is sort of relevant from you have a sort of an application in cell biology. You have some crowded intracellular domain. There's lots of stuff in the way, right? Like pictured here are these sort of reflecting obstacles. Well, it turns out one can prove that a single first passage time has this short time behavior on a log scale minus L squared over 4d, where d is the diffusion coefficient, and L is the shortest path from the starting location to the target that avoids obstacles. So L is somehow the distance of these blue curves that go straight to the target. And then the result of the theorem is that then this nth moment of the kth fastest first passage time has this large n behavior. Okay, so we can do it. We can do it on a manifold. So you have diffusion on this curved surface. You have multiple targets. Same story, but now L is the shortest path from the starting location to the shortest target, or excuse me, to the closest target. You have multiple targets, and this shortest path depends now on the curvature of the manifold. And then here's perhaps I think I really like I think is an interesting and somewhat surprising example. Suppose now you have diffusion with drift. So in this example, you have some drift b of x. Let's say it's a drift that's pushing you to the left. Okay, and then you have a space-dependent diffusion coefficient. So square root 2d, that's sort of the scale of diffusion, and then the space dependence is this sigma of x. And let's say that's the gray and white regions here. So we'll say the white ones are slow diffusion and the gray regions are fast diffusion. So what does the theorem say? So here's your target and here's where everyone starts. So what does the theorem say? So these are just 15 paths of typical searchers. Right? So what do? They just get pushed to the left because they have the drift. Right? So these are typical searchers. But what does the theorem say? The theorem says that the fastest first passage time has this nth moment behavior, L squared over 4d log n, that same formula we've already seen, what I'm sort of calling a universal formula. But now L, what's L? L is the geodesic distance in the Riemannian metric induced by the diffusivity matrix sigma transpose. So there's sort of two things to point out to note about this. The first is what it does is the fastest searcher takes the shortest path to the target, where the shortest path is defined by the space-dependent diffusion coefficient. So what is this doing, right? This fastest searcher is sort of weaving in and out of regions of fast diffusion, right? So it wants to avoid these white regions where diffusion is slow, and it goes through the fast diffusion regions. The other thing to note about this is notice that this right-hand side here knows nothing about the drift. The point is, if you have many searchers, the drift is irrelevant. The fastest searcher will go straight to the target, completely independent of the drift, in this leading order behavior. Okay, and what else? Okay, so I'm pretty much running out of time. So the point of this slide was to tell you about there's lots of other questions one wants to ask. How does this leading order behavior doesn't depend on k, doesn't depend on size of the target, doesn't depend on the drift, and then the way that we want to incorporate those is looking at higher order corrections. We'd like to know what the distribution of this is, and we're able to prove some theorems about that. Will give us some higher order corrections. But I will skip that and maybe just go to the end. So this was lots of extra stuff I put in here that I thought I might have time for. But we can, point is, as I just click through it, I'll tell you that we can say some things about some of these higher order corrections. And maybe I'll just end with this, some final thoughts about extreme first pass, or extreme statistics, extreme first passes time. So I think that this should cause us and perhaps to think about when we're trying to understand a time scale on the problem. It's very common to look at first passage times, but it's, I think this is highlighting that the number of searchers is a really important parameter. In particular, if you have lots of searchers, this fastest first passage time is going to be a completely different time scale than a typical first passage time. So I think just as as general as applied mathematicians, as we think about first passage time applications, I think something we need to consider and think about is the influence of possibly many searchers, and are we in this extreme first passage time regime, and trying to understand that. Other questions about how large does n need to be. So I'll just leave you with kind of an interesting fact. So for the human fertilization example, it's something like 300 million sperm cells, 3 times 10 to the 8. And I think for applied mathematicians, we hear the number n equals 3 times 10 to the 8, we think, oh, that's definitely large n regime, right? That's large n regime for sure. But it's interesting that if that sperm count is reduced by a factor of about 4, then infertility ensues. So somehow it's like just right that 300 million is enough, but 75 million is not somehow. So that's it's kind of an interesting fact. And so from a mathematical perspective, that means we really understand like how this scales with n and how large n needs to be in this extreme regime. Let's point out these extreme first pass times reduce variability, so the coefficient of variation vanishes as an implication of some of this work I talked about. Also, extreme first pass times reduce the effect of crowded environments. So, if we're modeling some situation, we're modeling maybe diffusive search in some crowded domain, right? Maybe we have all these obstacles in the way. It's nice mathematically to get rid of all those obstacles, right? And just have diffusion in this kind of empty domain. And what the result of this analysis is that if you have many searchers, then the fastest searcher goes straight to the target. And so in the case of this crowded domain, that means this fastest searcher is going to weave in and out of these obstacles and kind of go straight there. And what you see then is that the fastest first passage time in this kind of unphysiological domain where there's no obstacles, and maybe this more realistic domain where there are obstacles, these fastest first passage times are going to be quite similar because these shortest geodesic distances are similar because you can kind of weave in and out of the obstacles. Let me just quit there. So just that's what I talked about. We think this work was done. The first project, the pharmacology project, was done with a really good undergraduate, Elijah Counterman, and then some of the extreme first passage time stuff was done with Jake Madrid, a really good graduate student. I'll thank the NSF for funding, and I'll just put up some references where some of the work that I talked about today, and I'd be happy to answer any more questions. Thanks for your attention.
Thank you very much for such an interesting talk. So please feel free to ask Sean questions if we have any. Paul, I think you can just directly unmute yourself.
Hi, I wonder if you included the correlations in positions. So, for example, the sperm, they're not independent. And if you think the front one, all the rest are behind it, might stop it going back more, that maybe that can give rise to a critical mass. If there are, just the fact you can't occupy the same space, if that will actually enhance the speed of diffusion. Because you're forced to go where no one else has gone.
Yes. Yeah, that's a terrific question. So in this analysis, everything I talked about today, we're assuming independent searchers. So there's no interactions. But you're right. I think that's right. So this student Jake Madrid, who I did a lot of this extreme first passage time work with, this is exactly what he's working on right now. Is trying to understand these first passage time problems with multiple searchers where they have some interaction. So he's looking at the case where they have hard sphere interactions, so they can't occupy the same region of space. He's trying to understand that. So yeah, this is a very I think an important and natural question to ask next.
Great, thank you.
And you're absolutely right that the intuitive result is exactly right, that since they can't occupy the same space, having lots of them means they tend to spread out, and so they're more efficient searchers. That's right.
Kind of.
I have a couple questions, if I may, not right now. I mean, I'm very impressed by this last result. I think it's very unintuitive that many searchers don't really depend on their dynamics other than the diffusion. And I was wondering, I had two questions. I mean, the first one is, I mean, what is the order of the correction? Is it 1 over log n, just like you showed? And so this first order approximation really requires huge numbers to be accurate. And my second question is kind of related to the example of sperm that you gave, that, divide by 4 the number of sperm and you become infertile. My question was, why is that the case? Is it related to the time it takes for a searcher to find the target? Do the sperm die quickly? What is the time scale of? And I'm looking at the publication list right now and was wondering if that was what you studied in the Science paper this year.
Great. Okay. Yeah. So yeah, thanks for your questions. The first one. So in the large N limit, the fastest first passage time is independent of the drift. But you could think about this problem somewhat as a competing limit problem. So here in the left, I have a small target. So suppose the target size is epsilon. And so the analysis says if I take n to infinity, then the fastest first passage time goes to 0. And in fact, the leading order is independent of the size of the target epsilon. On the other hand, if I fix the number of searchers to be anything I want, and I take the size of the target to 0, then the fastest first passage time vanishes. A similar thing here here's I have diffusion in a potential well, right? So you have effectively you have a drift pushing towards the center of the well, and the same sort of story holds, right? If I can have the drift as strong as I want, that is the deepest potential well you want. If I take n to infinity, fastest first passage time is going to vanish, and it's going to vanish independently the leading order of the depth of the well. On the other hand, if I fix the number of searchers, I take the depth of the well to infinity, then the fastest first passage time diverges. And so when suppose one wants to know, are you in kind of this slow escape regime where a deep potential well or a small target, or are you in the fast escape regime where n is large? We have some preliminary, we have some results on that. In general, I think it's a hard question. Let me just, maybe I can show you a plot which should give you a little bit sense of it. So we can show, well, so these are the order of the corrections. So I'll just say the next order correction is log n over log n. So you're right that n does need to be very large for this stuff to really kick in. So here's a plot where I have n on the horizontal axis, and then I have expected value of fastest first passage time. And so this solid curve is the numerics. And in this problem, I have diffusion in a sphere with a small target at the origin of radius epsilon. Right? And so the analysis I didn't show you is that, so here's the large n regime, it goes like constant over log n. The smaller n regime, it goes like expected value of the single first passage time over n. So it decays like constant over n. And then it transitions. These markers are some theoretical estimates of the transition. And let me show you some more curves for smaller epsilons. So you can see here, so epsilon equal 10 to the minus 3, that's in the red curve. So that's the situation where you have a very small target, right? And so there, for at first, where n is not too big, it decays like a single first passage time over n, right? So it decays like constant over n. And then eventually for large enough n, it saturates sort of, it can't has that fast decay, and it saturates at this constant over log n. But you can see, in this case of a, kind of a target size of something like 10 to the minus 3, you're not in a login regime until, very large number of searchers.
Right.
So I hope that kind of gives some answer to your first question. And then relate to the second question about inactivation is, so here's a theorem. This is sort of a main theorem of this science paper I put on the last slide, is, and this was work was inspired by some work that some others did, but here the story is, you're not looking at the fastest first pass time out of many searchers. Instead, you suppose that each searcher can be inactivated, it can die at some rate. And you look at, suppose that they have a fast death rate. In this case, lambda is this inactivation rate or this death rate. And you look at what's the first passage time, I have the nth moment, but whatever, you have the first passage time tau, conditioned that you reach the target before this inactivation time sigma. And it's a similar story that in the limit of a fast inactivation, all that matters is the shortest geodesic distance L to the target. So this is sort of the same picture as before, but the story is a little bit different. Before, by having many searchers and looking only at the fastest first passage time, you're filtering out the slow searchers. But the same sort of story holds that if you have a fast inactivation rate, they die at a fast rate, you're filtering out, and you ask, what's the first passage time condition you reach the target before the searcher dies or is inactivated? Then you're filtering out searchers which don't go directly to the target, which we don't have this geodesic distance. So it's sort of the same type of result. I should admit, this result on inactivation that we did in this science paper was really motivated by this nice paper here I listed at the bottom, where they're looking at this problem in real cellular geometries. Really nice piece of work.
Okay, so would you think that the sperm problem is really that, what is the lifetime of sperm? So I don't know, it's a completely random question. I'm not sure you.
Yeah, I don't know. Yeah, I don't know. So yeah, whether that factor of 4 decrease in the sperm cell count, why that induces fertility? Is it because is it doing more to the death rate or sort of the fastest searcher out of n versus n over 4? I'm not sure. I'm not sure it's known, but this reference which I gave earlier, this PRL reference by Redner and Mearson, this is another nice kind of work that motivated a lot of the stuff I talked about, where they're sorry to flip through all these slides, but I just want to put it up. Yeah, the bottom of this slide, mortality, redundancy, and diversity in stochastic search. So they're looking at some of these competing effects of mini searchers, but then they have a death rate and how those things, and they're specifically motivated by this this sperm cell application.
So if you're looking for the first passage time of a narrow target, don't do Monte Carlo, right?
Yeah. Yeah.
Okay, thank you very much. That's
Yeah.
all I have. That was very good too.
No, thanks.
Anna, I think we still probably have time for one more question. You wanna go?
Okay, thank you for the talk. I was really interested because I'm a developmental biologist by training, and then time is always the important factor. And then, but in our field, experimentalists, number of particle is always the topic related to noise. So it was really interesting to see new perspective. And I had a question, if you bring this perspective into gene regulatory network or something like that, would you expect qualitatively different behavior of the dynamics?
Yeah, I haven't thought much specifically about applications to gene regulatory networks. That would be something I would be happy to chat about, think about. I'll make two comments. So depending on the model of the gene regulatory network, you might be interested in probably a different stochastic process than the types of diffusion things I've talked about. And so I'll say that we did do, I think I have a sort of a bonus slide about this. Excuse me to flip through all these slides, but so we've done some work where the stochastic process is not a diffusion process, but maybe is a Markov jump process. So here's this really complicated diagram of a network, but the point is maybe it could be a schematic diagram of say a continuous time Markov jump process where you have a discrete state space, and you could do similar analysis here where you have some source node on the graph and there's one target node, and you look at if you have many searchers hopping around on this graph, how long it takes the fastest one to find the target out of there, and there the general result is sort of similar, but the actual mathematics is quite a bit different. Just kind of maybe to answer a more general question of like applying this in other models of first passes times, what really matters is what's the first pass time of a single searcher? What stochastic process is it following? Is it a jump process on a discrete state space? Is it a piecewise deterministic Markov process? Is it a diffusion process like I mostly talked about? The other just quick comment I'll make is you mentioned thinking about numbers of molecules in terms of stochasticity. I think we usually think about, okay, if you have a large number of molecules, the process becomes deterministic because sort of law of large numbers kicks in. And a similar but different thing is here. So here, if you have many searchers, the fastest first pass time does become effectively deterministic, right? It follows this geodesic path, and this coefficient of variation of the time vanishes. But it's sort of for a different reason. It's like it's more of a large deviation principle type reason, where instead of so it's like you're effectively, because you have many molecules, you're effectively sampling the extreme of the distribution, and becomes more deterministic there, which is sort of a different than the law of large numbers way we usually perhaps think about these types of things.
Thank you.
Alrighty, we will wrap up here for today. So let's thank our speaker Sean again for giving such an interesting talk, and everyone for your support and participation. So we will take a break next week and resume in 2 weeks. So hopefully I will see you all in 2 weeks. Take care, guys.
Thank you. Thanks, everyone.
Thank you.